I'm Nasko, Oskov. I'm in the Kirkland office, about 2-hour flight of here. And I've been working on Chrome for the last about 6.5 years on the security team, doing navigation, process model, and other security things. I want to give credit to Charlie Rice and Camille, who actually did this talk on the previous 2 occasions. They came up with most of the content. My job was to make sure that it actually is still valid and it's updated, because a lot of things have changed actually over the last year or so since the slides were originally created. So overall, what are we going to cover is life of navigation, basically a very simple case. As you type in a URL in the Omnibox, what does actually happen? How does it work? What causes a network request to be made? How do we choose a process? What is actually a commit? What is load? There's various terminologies that are kind of very specific to the navigation flow. And then we're going to cover also some more advanced navigation cases like subframes, back-forward navigation. Service workers are an interesting new development that makes things even more interesting. So without too much, let's dive into take a note. So this talk, as I mentioned, has changed through time because code evolves. This talk specifically would cover the M67 to 69 timeframe, which is basically M67 is currently stable, 69 is our tip of tree. And the reason I'm mentioning it is site isolation is the work we've been doing in our team for the last 4 to 5 years, and is currently the default on stable. Hopefully it's going to stick out, not guaranteed. However, even if it doesn't stick this time around, it will be the default. So we can assume site isolation is the mode we're operating, at least on desktop, and we're going to go to Android a little bit later in time. And as John in his presentation on Autonomy of a Browser talked about network service, it does exist today. It is not the default. However, it kind of nicely abstracts the network from us. So I'm going to focus more on how things are going to work in the future to make sure that we're forward-looking instead of backward-looking. And in general, you saw a bunch of boxes in the previous talk. Chrome is multiprocess, is becoming more processes. And in general, in navigation, we pretty much touch most processes. The browser process today is responsible for doing the user interaction, disk, network, although network is going to move away hopefully soon. And it manages pretty much all the other processes that are happening in Chrome. And then render processes are what takes the HTML, JavaScript, and converts them to actual pixels that the users see. And once input events come to the browser process and they're sent to the renderer basically mutates the visual, so the user thinks they're clicking on something that runs in a browser process. However, it is not there. Renderer processes are untrusted. We sandbox them as much as we can because all of the stuff that comes from the web, place we don't tend to trust, runs there, and if there's malicious code, they can exploit security problems and run arbitrary computations. And the interesting part in Chrome, from almost the very get-go, it could actually perform what we call cross-process navigations, meaning if we start a navigation in one process and we determine that its security level or the security properties are not the same as what we need, would actually spawn a different process and navigate to it. It is a very complicated state machine, but we're going to kind of glance over some of the high-level today. So basic Omnibox navigation is what we're going to start with. It is what happens when you type in a URL up at the top in the Omnibox. However, Chrome also kind of, Darren mentioned earlier, pioneered the fact that we have one box instead of 2 boxes. We don't have a search box with a URL box. We had one. So you could actually type in a arbitrary phrase, and in that case, instead of converting it to a girl object, which represents a URL in the Chromium code base, if we can't convert it to a girl, then we will actually make it into a query to your default search engine, construct a URL from that, and that's what we're going to load. So as the user types, we either convert to a URL if it can be, or we convert it to a query that we submit to the default search engine. Then we're going to pass that to what we call, there's an object called web contents. And web contents represents basically the white area that you see in the tab. It's basically where all the web content comes. It doesn't include the Omnibox. It doesn't include the tab. And most of the time, you can think of web contents as the tab in Chrome. However, there's a bunch of other uses. For example, if you have an extension that has a button up at the very end, and you click it and it pops a little bit of UI, that is another web content. The extension background pages also run in web content. So web contents are basically our container where you can spin it up and navigate it to some arbitrary URL and it runs stuff for you. And in most cases, the users see it, interact with it as a tab. So we'll mostly use it as a tab from this point of view. And then how does it become a rendered web page? Well, we take all of the data from the network, we give it to the render process, it converts it to pixels, gives it to the GPU, which displays it on screen. Very, very high level. Now, in terms of code, because you're eventually going to have to deal with code, we start off with web contents, which, as we said, basically represents a tab. The navigation controller is an object within that is bound one-to-one with web contents that basically maintains your session history. And session history versus browsing history are very different. Session history is tied to your current tab where you have a back arrow and a forward arrow and you can click back and forth between. This is your session history, meaning for that tab. Browsing history is basically all of the history of everything that you visited across all tabs. So navigation controller maintains per tab, so it's one-to-one correspondence with web contents. And then every document that we load from the web basically gets a browser-side object called renderFrameHost, and it has a one-to-one corresponding object called renderFrame, which runs in the render process. They communicate over IPC mechanism, either the classic IPC that we have today, or we're converting more and more of it to use Mojo IPC, which was mentioned earlier. So RenderFrameHost is not the only thing that actually would run in web contents. Actually, web pages today tend to be complicated. They have multiple iframes. They include code from other origins. And when you render a document basically has multiple frames, each of those gets a RenderFrameHost, and we think of them as a frame tree. And there's an object called frame tree that basically maintains the tree of all the frames and how they are how they have a parent-child relationship. And also, I wanted to make a note that a lot of us talk about web pages, and web page is basically everything that the user sees. However, we try to think more and more and push the Chrome code base more and more to use the abstraction of a document, because a document runs in a frame, and it can have subframes that run other documents. And when we talk about navigation, you can only navigate one frame or one document at a time. So the one-to-one correspondence of navigation is you go from one document to another document within the same frame. If you have a different frame, it's just a different instance of a navigation. So there are a bunch of threads and processes involved. So we're going to use this type of diagram to kind of sequentially show what's happening. We have the browser process UI thread. That's where a lot, or actually most of the navigation logic runs. That's where session history is maintained. That's where a lot of security state is maintained. The blue one is the network stack. I'm going to purposefully use the word network stack because it kind of abstracts what happens. Because today, the network stack runs on the browser process IO thread. Network service today, before we've launched it fully, runs on the browser process IO thread. However, it's going to run in a separate process. So what's important is the network stack runs on a different thread of execution from the UI thread or the render process. And it doesn't really matter for the sake of navigation, where does it actually run? And just to go a very, very quick overview of how timeline of navigation works, and we can delve into the details later, is the Omnibox is part of the browser process. When you type in something, we call it browser-initiated navigation because the browser is the one that actually starts it. It initializes, meaning that it takes the URL or the input, converts it to a URL, then calls a function called begin navigation. So begin navigation is where we say, hey, we want to start a navigation to this URL. From that point on, we're going to hop over to the network stack and say, hey, this URL is what we need to request from the network. Go ahead and start the request. And then when the response comes back, we're going to go back to the UI thread. We're going to get notified, hey, we have a response. Find me a process that needs to render this content. Then we would find the process, we'll create the render process frame if needed, and we'll commit the navigation. And this is kind of what confused me when I started on Chrome was I always wondered, what is this commit thing? It was not very clear to me. So hopefully I'll just demystify it a little bit. It's the point at which we have one document that existed, but we've decided, you know what, that's no longer the document we're going to display. We're committing to displaying this new document. And from that point on, everything is different. The URL changes, security properties change, all kinds of things change. And when the renderer, we send it a message saying, hey, commit this document that we received from the network, it basically echoes back and says, yes, I did commit navigation. And then the browser process is now in sync, knows that this is the committed document, and a lot of state basically gets updated. And it is very, very important point in time because all security decisions depend on what state is set at this point in time. And then at commit, we actually more or less finished navigation. So this is kind of another point of confusion. Navigation doesn't mean you click a omnibox, basically type the URL in the omnibox, and you wait for the page to load, and there's a spinner that spins at the top, and pixels start showing up, images start loading. This is not navigation. Navigation ends at the point where we said, this is the document we're going to start loading and update our security state. And from that point on, the loading phase comes in, where we start reading data from the network, we start parsing, we start loading sub-resources like images, JavaScript, CSS, and what so on. And only once we have continued loading and we're done, we tell the browser process, hey, load stopped. Therefore, we no longer need to spin the spinner in the tab. There's no progress bar advancement anymore. We're completely done. So let's dive into each of those states a little bit more. But overall, how do we actually observe navigations? Because most code actually doesn't need to implement navigation, but the code tends to care about what happens. And Web Contents Observer is the interface that you can implement that is one-to-one with a web contents, remember, like a tab. And it has those few methods that basically dispatch notification of what happens. So the first four did start navigation, did redirect navigation, ready to commit navigation, and did finish navigation. They all take an object called navigation handle. And you can think of it as kind of a read-only interface into the navigation subsystem telling you, this is what's happening. This is a navigation to this specific URL that has encountered these redirects or has the following properties. So basically, you can query that navigation handle object to understand more about what happened. And that the did start loading and did stop loading are the events that bracket a navigation and load. So the moment you press the enter in the omnibox, we dispatch the did start loading, meaning we've started loading something. We'll finish the navigation, we'll continue loading, and once we're done loading, we're going to dispatch the did stop loading, which stops spinning and basically tells us we're done with everything. So let's go first step. First step was we say to the navigation system, begin navigation. I mentioned navigation handle tracks the state and tells you what's happening. It does live only on the UI thread and basically gives you a glimpse into what's happening. Navigation URL loader and its implementation is what basically allows us, and it's the interface that we use to talk to the network stack. It is the one that we say, hey, issue a URL request for navigation, and then it gets notified, for example, something either failed or we started reading bytes, and basically is the channel that communicates across the network stack in the UI thread. And the navigation throttles are basically objects that we want you to implement if you want to interpose on navigations. At this point in time, we do dispatch the did start loading. Basically, something happened, we're starting to load. And then a little bit more about navigation throttle is, in general, web contents observers are read-only observations. You're not allowed, and you should not be making any changes to navigations. For example, if you wanted to cancel a navigation and reissue a different one, this is not, observing a navigation is not what you want to do. If you want to cancel a navigation, you can implement a navigation throttle. And this is the API that you use to actually mock with navigations. You can either say, hey, it's fine to just let it go. You can defer or pause. For example, if you want to say, hey, we have too many tabs. We don't want all the background tabs to be loading all the time. We can just pause the background tab loading. Once we've loaded everything else, we can resume and continue on. So if you want to pause the navigation, not let it proceed, to do some asynchronous type of work, this is what you basically say defer this. You can either cancel or cancel with error code and various other things. Navigation throttles do run on the UI thread as well. They have these 4 methods which tell you basically how the navigation is going through its lifetime. It tells you we're going to start a request. Maybe you don't want to start a request at all if you want to avoid sending cookies to a malicious website. It tells you that we're about to redirect to a different URL. Maybe you don't want the web to be redirecting you to data URL or to some Chrome internal URL. So you can stop it there. We tell you that it's going to fail a request because something happened and error occurred. And then we'll process responses. Once we've actually received the response from the server, we will tell you, hey, now we have data to do something. Do we want to proceed or not? So then now we're at the stage of where we're starting the URL request. Basically, the network stack, as I mentioned, runs on the IO thread or a separate process. It basically depends on how Chrome is configured. And it does the basic things of look up an IP address based on DNS, establish the TLS connection, make the request, gets data, and so on and so on. There will be networking 101. We'll delve a lot more in detail than this. But in general, we want to start a request and get data from the server. There's also redirects. So there's 2 types of redirects. Server redirects are what is handled by the network, which is a server returning a status code like 302 or in the 300 range. Usually says, this is not what you're looking for, go this other way. And basically at that point in time, the network stack would jump over to the UI thread, will tell you, I redirected from this URL to this URL, do you want to proceed? And then when we decide yes or no, if we decide yes, we can come back to the IO thread and say, the network stack, and say proceed with the next request. Those are different than client redirects. Client redirects are also kind of a little bit of a confusing thing because you actually end up navigating to a document, start loading it, and the document itself says, I'm not what you're looking for, go somewhere else. So basically, client redirect is where we've actually committed a document, and the document uses either JavaScript or HTTP header or HTML to tell you to redirect over somewhere else. And then, as we mentioned, navigation throttles can also interpose on redirects and prevent you from redirecting if you don't want to follow it. Ooh. Can we get rid of this? Sorry, the slides are a little bit easier to see. The black bar is covering. Basically, how you observe is you have Web Contents Observer did redirect navigation. It's an API that we call every time that there's a redirect. And just to quickly go over the timeline, as we started the URL request. We basically jump back and forth, if needed, multiple times between the network stack and the UI thread in order to process those. And then we go through the usual other flow. So when the response actually has started, so we followed all the redirects and the server starts sending us data. At that point in time, there can be multiple things. For example, if you clicked a link to an executable or some other format that the browser doesn't know how to handle, or the server says, hey, this is disposition attachment, you should download this thing instead of rendering it. What's going to happen is we're going to take that stream of data and we're going to basically offload it to Download Manager. We're not going to change anything about the current document because we'll end up downloading something. So we hand off the stream to the Download Manager and no navigation actually happens. Similar things exist like HTTP standard defines a 204 response, which the server can say, hey, I got you, but don't do anything. Just leave the old document intact. At this point also, we do MIME sniffing to verify that what the type, if there's a mismatch in the content type, we can try to infer what it might be. And also, at that point in time is where cross-origin read blocking comes in when it comes to security. We mentioned site isolation a few times. This is if a malicious process decides, hey, I want to request this document that is in a different origin that I don't have access to, we would actually block it as part of the network and never actually give it to the renderer to safeguard secrets. Also, this is the point in time where additional checks like safe browsing are run because now that we know that something has arrived, let's make sure that it's something that we actually want to commit in the render process. And at this point in time, the browser process expects us to commit this document. So in order for us to commit a document, we need to actually figure out where. And this is very key to Chrome's process and security model. We have various modes of operation, and there's various policies that govern how we pick processes. For example, same origin pages must be in the same process. If, for example, do a.com does a window.open and loads another a.com document in it, they have to be able to synchronously access each other's DOM through JavaScript. And that cannot happen if they're in separate processes. There's no way we can have synchronous access between them. Therefore, we put them in the same process. There are other cases where we don't have, we cannot actually share the process. For example, you go to evo.com and you want to also load Chrome settings. We don't want Chrome settings to live in the same process as evo.com, because if evo.com has arbitrary code execution and has the ability to render Chrome settings, that gives us the ability to change your settings, like download location, cookies, pretty much anything. So we don't want Chrome internal pages to have the same, to live in the same process as untrusted web content. And then we have a bunch of flexibility in our process model. We try to get new process if we can. That gives us the benefit of starting with a new process gives you clean slate. You don't have memory fragmentation, you don't have contention, so it is much nicer to start executing in a new blank address space. However, we avoid swapping if scripting, as I mentioned, would be broken. Therefore, we try to keep it in the same place. And Chrome has a process limit that we kind of impose on ourselves. It is based on the amount of RAM that the machine has. We pick, here's an arbitrary calculation of how many processes we want to use. Once we hit that limit, we try to actually reuse existing processes as long as they match in their security properties and they're compatible with what we want to render. We'll try to use it in a semi-random fashion. And then when we're moving cross-site, that's where site isolation comes. We must change processes because a.com is not the same as b.com. And let's go a little bit over in the concept of what is site instance. So how we pick processes and how we do process decisions is heavily based on this class called site instance. And it represents basically a group of documents or pages that share a process. So for example, as I mentioned, a.com does a window.open to another a.com. They'll actually end up using the same site instance. They'll be placed in the same process and everything would work correctly. And sometimes we want to basically put them separate, just like we said, a.com and maybe your Chrome settings. But also with site isolation, when we have b.com, open another window and navigate that to c.com, we actually, even though they're related tabs and they should technically stay in the same process, we know that they can never, because they're cross-site, cross-origin, they can never reach each other through synchronous means. Therefore, we can actually put them in a separate process. If everything is asynchronous, we could just route it. And this is what we've actually implemented. If you post message from B to C and they run in different processes, we'll actually route it from one process to another. And basically, site isolation is what ensures that sites that must not share, never share a process, and they're properly allocated into their own site instance. And as I mentioned, swapping processes is key to Chrome's security model. The way it manifests is we want to create a new process to get different security properties, and we would do it basically at the time of receiving the network data. And we'll say, hey, this is a new origin after all the redirects. We know where we're going. Therefore, let's pick a process. But we also know that the network, going to the network is slow. Like, especially if you're going cross-continent, it's going to take a few milliseconds at least to get back and forth. And as we start a navigation, we know that the URL you're trying to go to. So barring something that redirects you across to a different origin, we kind of know what type of process we need. So we have an optimization that we call a speculative render frame host, where we try to start the process and create the frame in parallel with the navigation. So by the time the network response comes back, the process has had a chance to actually initialize and be ready for us. And how do you observe this? It's not visible, but it is the stage where we say it's ready to commit navigation. So code in the browser process that wants to initialize state, for example, extensions, if they want to say, hey, this is going to be a frame that or that hosts an extension document, we need to set up extension bindings. We need to basically prepare it to be in an extension context. This is, for example, the time where they can say, okay, now that we know that we're ready, we're going to send a bunch of IPCs to the renderer to prepare for this particular context. So how does it look on the timeline diagram? As we receive the begin navigation, we would actually start the speculative process. And then we'll follow the usual redirects and reading the response data from the network. And then we're going to tell later on, hey, we've created this ahead of time, commit into it. And then from there on, we receive the commit acknowledgement, and we're ready. So what happens when we actually tell the renderer to commit the navigation? Today, we've done a bunch of refactorings. By the way, I didn't mention, but you would see across the code base something called please navigate. It's how navigation works today, but it's not how it used to work. The render process would have to go back to the browser process to get data and back. However, as we've wrapped up and we're still cleaning up please navigate, what we do is when we receive the data from the network, we actually start writing it to a Mojo data pipe. John mentioned earlier, data pipe is a kind of core concept to Mojo. And when we start receiving the data, we start writing it to that pipe. The pipe basically accumulates it. And then with the commit message, we actually pass the other end of the data pipe to the render process, and we tell it to commit the navigation. At that point, the renderer can just start reading it directly, so we don't have to have extra hops to the browser process. And we know that the renderer has committed, but the browser doesn't know quite yet. So but it's part of Blink processing the commit message. There's a lot of complexity. I'm just going to gloss over. I'm going to say that we're refactoring it to be much, much easier to read. It involves frame loader and document loader, but we're separating it such that it doesn't involve all the old concepts that used to exist prior to please navigate. And now we have separate stages that we say either start a navigation or commit a navigation, and things are much, much simpler. So when the renderer has read and committed the navigation, it's created its new document object, its new document loader. It goes ahead and sends back to the browser process a did commit provisional load. And now it is actually a Mojo interface code. It's no longer an IPC. So when that comes up to the browser process, it comes to the UI thread. And this is the key moment in navigation. This is at the point where in the browser process we say, we've moved to the new process if we needed to. We've moved to the new origin. All of the security state has changed. We pretty much try to invalidate all module interfaces that used to exist in the past. We create the new session history entry saying we've now navigated here. You can go back to your previous state. We update the URL bar in the Omnibox so it's seen. And pretty much this is the key point where navigation is complete. We've switched security state and we're ready to continue loading the document. How do you observe that is through Web Contents Observer did finish navigation. And I want to mention did finish navigation is kind of the ultimate end of a navigation. Whether it was successful, unsuccessful, it was canceled or not, we always dispatch did finish navigation. And you can check the navigation handle methods. Basically, it's state to say, hey, is it committed? Is it committed on an error page or a regular document, and so forth and so on. So just to kind of show it again, we go commit, gives us a frame, and then we continue into the loading stage. Now, the loading stage and the load stop involves quite a bit of work. Later on, you're gonna hear life of a pixel and life of all kinds of other things that would cover a lot more about how actually the rendering engine ends up producing pixels. But the loading phase basically entails loading all sub-resources like images, CSS, JavaScript. Those are basically made directly to the network stack. As John alluded, we don't want to go back to the browser at all. And then when we say load stop, everything stopped. We don't need a spinner, so we're good. This is the did stop loading event that we get at that point in time. So I'm going to gloss very quickly through the advanced cases because we don't have as much time. However, there's the before unload and unload events that we dispatch to web pages. the before unload is, as we know we're going to start a navigation, we can display a prompt to the user, say, hey, you're about to lose data or something happens. Do you really want to proceed? The user can cancel, at which point we don't proceed with navigation. And how they look basically is we go from the browser, we say, hey, run the before unload handler if there's one. And then we say, hey, sure, proceed with navigation, or no, don't proceed, at which point we cancel. And then from there on, the flow is exactly the same. So we also distinguish between render-initiated navigation and browser-initiated. Browser is when the user does something like omnibox, bookmark, right-click, whereas render-initiated is basically script or anything that comes from untrusted process, so we tend not to trust these as much. And you will see a lot of browser code, basically reasons should we do this based on whether it's a browser-initiated or render-initiated navigation. And the render-initiated navigation in terms of the timeline actually starts in the renderer. So basically, for example, if you do a link click, basically Blink will say, hey, I want to run the before unload handler, and if that is okay, go to begin navigation and kick off the navigation flow. Subframes are very different beasts. In most cases, they're almost the same. However, the one thing that is interesting is that the first document that commits doesn't create a new session history entry. It just kind of stays there. And when you click a link inside it, that starts adding to your session history. With out-of-process iframes and site isolation, we now know that A.com and B.com can run actually in separate processes. We mentioned session history versus browser history earlier on, so I'm going to go a bit quicker. And just to show you a little bit of how session history actually works, each frame in that frame tree has a document. And let's assume that we have this session history where we've got from one document, we added some frames, and we went forward, and it kind of came back to the middle. Now, if we decide to click a link in document that is red in color, all of its subframes will disappear. We're going to tear down the old document and create a new navigation entry where we actually replace all of its subframes. So whenever you have forward history and you do a new navigation, all of forward history gets basically purged and nothing stays there anymore. Navigations can fail. We've covered some of these, like downloads or 204s or network errors. And just to show you in the diagram, it can fail because the user canceled it. It can fail because it was blocked by navigation throttle. It can fail because network error. It can fail because the redirect was blocked, or it just ended up being a download. So lots of failure points in the timeline. And then I wanted to mention service workers because they're a fairly new addition to the platform, and it is where it impacts us is that we actually need to hand off the navigation request to the service worker first, because service worker is more or less a proxy the developer can write that runs inside the browser and intercepts pretty much every network request. And what that means is that in the timeline, we need to basically give the service worker a chance to process the URL request, either cancel it and return it from cache, or completely cancel it, or basically say, no, go to the network and fetch the resources. So just overall recap, we went through simple navigation on the Omnibox. How do we go about starting a network request? What does actually commit versus load stop is? What is navigation versus document load? And I glossed over quickly over some of the more advanced cases, but if you have any questions later on, feel free to ping me at any point in time. So in terms of questions, let's look at the Dory. Okay, so what are the difficulties in having this site isolation in place? What was not taken into consideration from the beginning, and if that helps address potential security issues? So it does say, does address security issues. Actually, site isolation is our only real answer to the Spectre and Meltdown vulnerability, well, technically Spectre, CPU vulnerabilities. Why was it difficult? Well, first of all, it required rewriting all of Chrome. It took us about 5 years to rewrite all the parts in order to be compliant and work in the same way. We had to take session history, move it from the render process to the browser process. We had to create a frame tree instead of the render process up in the browser process. Printing a page needs to basically get all the frames from separate processes and kind of stitch them together. So it is a lot of code churn. And yeah, go ahead.
I was just curious, is the issue there that those were tightly connected because of the WebKit heritage, and then you had to tear them apart?
Yeah, so basically the question is that because of the WebKit heritage? And yes, it is. And actually, we could only do site isolation in under-process frames once we actually forked off of WebKit, because we just couldn't change WebKit in the way that we wanted it to work. So we had to fork first and then have to rewrite everything, and also not just rewrite it, but rewrite it such that it is as performant and as good as like regular mode. So this was fairly challenging and took a little bit of time. So had an opportunity to observe the browser-side navigation project in progress. How much improvement did it make in terms of speed and security? So in terms of security, I don't know that the new architecture made much of a difference, other than we have better layering, better logic, so we can reason about things more correctly. Also, as we were developing it, we've learned a lot on other bugs that we've seen in the past. So we started adding checks to say, hey, we believe this should never happen. Well, we started actually hitting some of these, so we fixed a bunch of bugs because of that. In terms of speed, we actually improved some of the speed metrics, because now we can start the process at the same time as we're making the network request. So on machines that are, on slow networks, for example, we would have the process ready to go. So it was also one of the main motivations to start the refactoring, was we wanted to parallelize those two pieces. So does a web contents object persist across navigation? Actually, this is a very good question. Not only web contents persist, but actually render frame host itself can load multiple documents, assuming they do not change its security properties. So this is one of the confusing parts, which we want to actually change Chrome's code base to have a pure like document instead of frame and a document. So today, web contents persist across everything, basically the lifetime of a tab. Render frame host lives for potentially multiple navigations if you navigate within the same origin. And then we change to a new render frame host if you need to go to a different process. Basically, render frame host and the process are kind of one-to-one. Let me just go through the asked question, and I'll go live questions. Oh, sorry, and if not, no, so it's not. John mentioned network service out of process didn't result in more hops, making the previous browser rendering. But how do you say the UI thread is involved so it's 3 processes? So today, even without the network stack, it is always you go from the renderer process to the browser process to the network stack. So there's always those 2 hops. Whether that last hop is going to the IO thread or goes to a different process, it's still a hop. So even in today's architecture, without the network service, there are multiple hops involved in navigation, actually.
Right, but hopping a thread or hopping a process, is that the same performance?
I don't know. I haven't measured it personally. However, there's a you need to serialize the data across a thread hop, and you have to do it over a process hop. So I don't know specific data, but I would assume that they're not terribly different. And then, does the selection rendering process vary between desktop and mobile, or is it strictly memory resource based? It's actually, memory is one of the inputs. Actually, security comes a lot more often into the in the calculation whether we need to do it. And yes, at this time it differs because we enforce site isolation on desktop, but we don't quite yet on mobile. So on mobile, we're not going to change site processes and sites as often because we're resource constrained there. Question.
My question is about render-initiated navigations. Where in the and maybe you mentioned it and I missed it. Where in that timeline does that happen? Like, does the renderer just tell the browser, "Hey, I'm navigating now," and then you start from the very beginning of that graph?
So in that graph, basically it does literally say begin navigation to the browser, and it just goes into the same flow that the browser initiated comes in. They all come into that endpoint.
Great, okay.
Yeah. And sorry I'm out of time, but I'm going to be hanging around here most of the day. Feel free to ask me questions. Just like John, if you have any questions, ping me on chat, email me, and I'm happy to help. Thanks.